In this objective, we're going to look at 5.10 multi-step reaction energy profiles. So the learning objective states that we should be able to represent the activation energy and the overall energy change in a multi-step reaction with the reaction energy profile. So we've been looking at a lot of energy diagrams that have been just one single elementary step. So multi-step will have multiple activation energies based off the multiple steps that correlate with that mechanism. So multi-step, so the knowledge of the energetics of each elementary reaction, the mechanism, allows for the construction of an energy profile for a multi-step reaction. So the exact mechanism by which a multi-step occurs can be determined by multiple observations. So the direct evidence of that intermediate, also the rate law by which the reaction occurs. So a multi-step reaction can be illustrated by a reaction energy profile only if the individual energy of each steps are known. Because here's the thing, you need to know the activation energies for these reactions occurring, okay? Because when it comes down to it, if you don't know that, you can't really be using this reaction energy profile to its best potential. So if you look at this one right here, we still have reactants and products, and you will notice at the bottom part right here is where our intermediates will lie. Okay, this would be the newer part of looking at these reaction energy profiles based off previously. And you can see that there are two transition states, because remember, the tops of those peaks indicate that your particles just got broken and they're trying to reform. Okay, and so here this would be indicated as activation energy 1. And then this would be denoted as activation energy 2. They would be different values. They do actually look relatively the same, but I will tell you for the test, they will be denoted as either longer, shorter, based off activation energies. Real quickly, just recall previously that we had learned that the slowest step will tell us the rate law because it affects the entire reaction. So that's why we call it the rate determining step. It is taking the longest for it to occur, and the others end up being super quick and fast. So the slow step really shows us what the orders are with respect to those reactants. Biggest thing here, since it's the slowest step, you got to look at the highest activation energy peak. This will be the slowest step. Okay? All right, so let's look at an example right here, okay? On the graph, illustrate an endothermic reaction that proceeds via a 3-step mechanism with the second step being rate determining. I'm actually just going to do this one with you just so we can put pieces together. If you do want to pause the video and try it out yourself, you're more than welcome to, but I'm going to dive into doing the reaction now. So endothermic reactions means that your reactant energy will be lower than your products. So here, that's where I'm going to first start. So here, reactants, I'm going to show products over here. Okay, so it tells us that the second step needs to be rate determining. So that needs to have the largest hump peak activation energy. This is a 3-step mechanism, so we're going to need to show 3 humps total. So each hump indicates one elementary step. So here I'm going to show my first reaction, first step. Then on the second one, I'm going to be very dramatic with it. So there's the second one. And then the next one, I'm just going to show a little peak like this. Okay, so here, activation energy, that's fine. Then this would be activation energy 2, and this would be activation energy 3. We would have our intermediates right here. You don't need to label them. I'm just doing it right there. I will say the delta H, remember we always take the difference between products and reactants, would be right here, and it would be positive. Positive. There we go. So you can see, why is that not working? Hold on. I cannot draw. It's fine. There we go. So you can see in this one right here, I made the second step the highest, longest activation energy, showing that 1 and 3 end up being way faster than the second one. Okay, so this would correlate with this problem. And I have seen some free responses on the AP test where you need to show a two-step mechanism, making it overall exothermic, stuff like that. So make sure in your problem set you do these types of reactions to make sure that you have this down to get those easy points, okay? Because what they're going to be looking for is generally it's 2 to 3 points. Like, did you put 3 peaks? Did you show that the first or second was the rate determining step? Did you put the reactants lower than the products to demonstrate endothermic? They're going to be looking at a lot of points in different parts of you drawing that graph.